Hi. So hopefully this works this time. But I just wanted to talk to you about internal resistance and EMF just because it is new and I don't think reading the notes is going to cut it for your understanding. So I'm going to show you what I'm talking about first of all here, and then we will draw diagrams and whatnot. Okay, so I've just got a wee battery here. Now a battery will have a voltage stated on it, and that is called its EMF, or we call it its EMF. So what that actually refers to is like the voltage that you would get if you just plugged your voltmeter in across this before you put that into a circuit, so before there's any current actually flowing. However, as soon as you plug this into a circuit, or as soon as you have current flowing through this, you'll notice that the voltage that you get out of a battery or any power pack is actually lower than that EMF. And the reason for that is that there is an internal resistance within this which like uses up some of the volts in the current getting through. So yes, the current picks up all the volts that are stated in the EMF, but it uses some of them up just in making their way through the battery itself. So if I plug my voltmeter in just across this, oh, I've plugged them in the wrong way, then okay, so we've got 1.56 volts whenever there's no current flowing. So this battery is literally just sitting here, and this voltmeter is just reading the potential difference across the two terminals. So 1.56. Now, as soon as I allow current to flow through this battery, we'll notice that the 1.56 is actually going to fall. Oh, there now it's like changing to 1.57. So I'm just going to set up a wee circuit here, and then we'll plug the voltmeter in again. Okay, so I've just plugged in a wee bulb. Now this battery isn't powerful enough to actually light the bulb, but now we have a current flowing. So if I plug my voltmeter in now, then we should see that it's reading a lower voltage. So now it's reading 1.46 volts. So the reading that this is taken, or that this is showing now, is how many volts are actually coming out of this little battery here. So there's less coming out than there was whenever it was just sitting there before there was any current flowing, and that's all down to the internal resistance and what we would refer to as the lost volts. So like the voltage that is used up with the current just trying to make its way through the battery. So I'm going to show you that with a wee circuit here now. Okay, so we have our power supply. I'm just going to draw it as a cell, right? Now this cell will have an EMF, and we just will refer to that, or we'll use E for that. So it will have an EMF of E, and that is the maximum number of volts that this thing can ever supply, and it's only ever going to do that whenever no current is flowing. So this is the EMF. That'll be like the voltage that is stated on the battery. Now we're going to have a circuit. So the way I'm going to draw that is just to have like a resistor and call it R, and this is just representing like the entire circuit. So like no matter what was going on in here, all of it can be combined into one resistance. The way that we tend to draw this is like just draw a resistor in series with our power supply. So we tend to draw a wee dashed line around that to show like that this is internal, this is in it. So this wee dashed line is showing like, oh, this is the battery, right? And the internal resistance, we use VR for that. Okay, so that means that the volts that are picked up from the power supply that are stated on the EMF, they're going to get delivered to this, but they're also going to get delivered to this, as in some of them are going to get used up going through here. So if we were to plug a voltmeter in across here, this is going to always read how many volts are being released. I don't know if that's the right word to use, but how many volts are coming out of the power supply, like how many volts we get from the power supply. So we call that the terminal voltage, or the terminal PD. And then that is really the voltage that's going to be across that, because this is the only thing in the circuit. And then the voltage that's used up across here, we tend to refer to it as wee v, like a wee small v. So if you remember the rules for voltage in series circuits, the voltage that the current picks up from the power supply gets delivered. So if it picks up 9 volts, it delivers all 9 volts before it arrives back. So that is the EMF. So now it's delivering some to this, but also to the internal resistance. So the EMF, the stated voltage that's on a battery or a power supply, is going to be equal to the number of volts that it delivers to the circuit, so the terminal PD, plus these volts that are used up in getting through this internal resistance. So this is the EMF. This is the terminal PD, or the PD that's going to be delivered to the circuit, or the external circuit we tend to call it. And this is the, I'm going to write lost volts. Okay, so they're the volts that are used up just by the current trying to get through this, trying to get through the power supply. So those ones today are probably sick of me saying this. I like to start off always from this because this is easy for me to remember, and then all other versions of this equation can come from that. So we know, oh here, I forgot to say, there's going to be current coming around this circuit, and the, sorry, the cleaner just came in there, so I've forgotten what I was saying. I've had to pause it. What was I talking about? The current. So yeah, so the current that's traveling here is going to be the same everywhere. So the current that is going through this load resistance in the circuit is the same current that's going through here, because remember, series circuit, current doesn't change. It's literally a count of the electrons, so it can't change. So we can replace this with E equals IR, as in V equals IR. So I've just replaced the V with IR, plus with, for this wee V here, it's the same current, but it's that wee resistor R that we call it, I call it wee R, that's very Northern Irish, but we use a small r for it. So this is one of these equations where it depends what the question gives you, like what version of it that you use. So because this is the same current, then we can factorize it. So E equals I upon R plus R. And actually, this version here generally is the one that you use most often in your in the questions, this one here. Now in the examples I didn't just start with that because I was trying to show like we can always start from here and figure it out, because this is quite awkward to remember, whereas this is nice and easy to remember. So I'm going to say this is in your data sheet, but they've worded it weirdly in your data sheet. They've used like an amalgamation of these two. So they have used E equals V plus IR, but not even that. They've rearranged it and they've given it to you, I think they've given it to you as V equals E minus IR, as in the volts that you get out is the EMF of the power supply minus the voltage that's used up and getting through, but they've written it as IR. So this version here is like the data sheet version. Okay, right, I want to just I'm probably going to fly through these notes here because that really was what I wanted to talk to you about here today, just what on earth we're talking about, but I'll fly through the notes in case because there are things in there actually I just want to point out. Okay, so hopefully you have read through these, but basically it's just saying that sources of EMF have an internal resistance, so some of the EMF is used up in trying to make its way through the battery, if it's a battery. So the internal resistance has got two effects. One is that as more current is drawn, then that means there's going to be less voltage from your power supply. So that's what I was trying to show you with the wee battery at the start. I've put it away now, but whenever we had our battery and we just plugged our voltmeter in, we got, what was it, 1.56. Then as soon as current was starting to be drawn from that, the voltage that we got out was less. It was 1.46, I think. So that's all that is saying. And it means that your source of EMF, your battery, is less than 100% efficient, because in trying to make its way through that internal resistance, you're going to be transferring energy to heat. So some energy is dissipated as heat within it. This here is important. So the voltage stated on a source of EMF is the voltage measured across its terminal when no current is being drawn from it. So that might come in handy in questions. Down here you have pictures of this anyway, but that's just the wee circuit I was talking about a wee minute ago. And just in case, because like this is new, so if you were looking at that thinking what on earth is even going on, hopefully me talking through that other wee one has helped with that. So I'm going to skip on here, and then this is all the equations. Oh, one thing I did forget to mention there whenever I was talking about those equations was this other one. So I'll just go back to this. Right, the time that you are going to get the maximum current out of this circuit is going to be whenever the resistance is the lowest, because like if you increase the resistance, then the amount of current that is allowed to flow is going to decrease. So if we were to rearrange this and make current be the subject, so I equals E over R plus R, right? Well, you're going to get your maximum current, so I max, whenever this load resistance is 0. So you just get that. So this can come in handy, and that's the type of thing I would forget. So I did forget to talk about it when I was saying to you, but yeah, it's very easy to forget that wee one. But like, you can, if you think it through logically, you're going to get the maximum current whenever the load resistance is 0. So that just means that is 0. So 0 plus R leaves you with R. Okay, so that is that. This little graph here is just showing that the power that you're getting transferred from your energy supply is going to be maximum whenever your load resistance is equal, numerically equal, to your internal resistance of your cell. Okay. Okay, I'm over the page here on page 67, and this is really just the principle of conservation of energy, as in energy in equals energy out, or power in equals power out. So the power released by the chemical energy in the battery is going to equal the power dissipated in the internal resistance of the battery plus the power delivered to the external circuit. And then I've just replaced this with P equals IV, but here I've used E instead of E. Okay, these examples aren't the nicest. This one here is just a wee weird one. So when current is drawn from a dry cell or cell, when a current drawn from a dry cell is 1 amp, the voltage across the cell's terminals is 0.5 volts. When the current drawn is 0.5 amps, the terminal PD is 1 volt. Calculate the EMF of the cell and its internal resistance. So we've got two different situations here. We've got situation 1, which is whenever the current is 1, the voltage is 0.5, so that's why I've listed these two together. And then our second situation is whenever the current is 0.5, the voltage that we get out is 1 volt. So if I start back here again with E equals V plus V, oh sorry, should have said, it's asked us to get the EMF and the internal resistance. So these two things are going to be the same in both of these situations. It's just that these two have changed. So E is V plus V. We know V is 0.5. We know the current, but we do not know the internal resistance. So I've replaced we V with I, we R, okay? And then I'm ready to substitute my numbers in. So E equals 0.5 plus 1R, 0.5 plus R. I've done the same here. And then we've basically got two equations, two unknowns. But rather than take them one away from each other the way you would in maths, I've just put them equal to each other. So if E is equal to this, but E is also equal to this, then I can say that this is equal to this. I'm not going to waste your time going through the algebra here. You can follow it yourself. Anyway, we end up getting the internal resistance to be 1 ohm. Then substitute that back into either this or this, and you'll get the internal resistance. So that's what I've done down there. Okay. Example 2. So this one here is quite a good one. It's making use of the maximum current we fact there. When a 12 volt battery is short circuited, so short circuited means there's no resistance in your circuit. So that's whenever big R, the load resistance, is 0, which means you're going to have your maximum current. So I initially wrote that down. I max is 6 amps, and it's a 12 volt battery, so that means E is 12 volts. Then it goes on to ask, what current would you expect to flow when the load resistor is 4 ohms? So whenever whenever big R is 4, what is I? Well, forget this for a little second. If you were to go on and use E equals V plus V, substitute for IR, and get like this is the version we end up using. So you would get to a stage and you would realise, oh, I don't have enough information here. I'm going to need to figure out the internal resistance of this cell. And you can, like, if they've given you this information, you can guarantee you're using that wee Imax equation. So if we use Imax is E over we R, then we can get the internal resistance of the cell. So now we have it, we can substitute in, and we've got everything that we can put into this, where I then is our only unknown. And then we get 2 amps. I know I'm going through these examples quickly. I'm telling myself you will already have read through them, but hopefully we're okay. Ask me please if you're stuck. Right. Example 3, instead of making a list of information like I'm always going on about, I actually find it often much easier just to draw a wee diagram. So 3 identical cells each have an internal resistance of 0.5. They're connected in series with each other across a load resistor of 1.5. The EMF of each cell is 2. Calculate the current drawn from the battery and the power dissipated. So drew my cell, there's my 3 cells. If each of them has an EMF of 2, then whenever they're connected in series, the EMF of them all together is going to be 6. Each of them has an internal resistance of 0.5, so altogether the internal resistance is going to be 1.5 because there's 3 of them. The load resistor is 1.5, and we've been asked to find the current that's been drawn from the battery, so I, and the power dissipated, so we're being asked to find the power here. So once we get that drawn, like there's no way I would attempt this question without drawing a wee diagram. I would totally mess it up. So once we get that drawn, then I like to start with E equals V plus V, but you don't have to. Again, it's this version we end up using. We can start to substitute our numbers in. So we know E is 6. We know, or sorry, we're looking to find the current. We know the load resistance is 1.5 and the internal resistance is 1.5. Solve that and you get 2 amps. Now, then we could, like you could go on and use V equals IR to get the voltage across this and then do P equals IV, but might as well save a step. If we have the current and the resistance, we can use P equals I squared R to get the power and we'll get the 6 watts. Okay, this last example is a stinker and I ended up squashing it too much on my page. I'm raging with myself. So let's look at it. I was trying to write my thought process here for you, so hopefully it's worked. This I drew whenever I recorded my field video. So when a 2.5 ohm resistor, so this is what I'm drawing up here, is connected across a battery of EMF 6 volts, the terminal PD is 5 volts. So EMF is 6 volts. We've got our internal resistance here. We've got our load resistance of 2.5 and we know the terminal PD, so the voltage that is getting released from that power supply is 5 volts. So it's all going here. So 5 volts are going to this. The terminal PD is 5 volts. So part A is a wee strange one. It's actually nothing to do with any of that, but I'll come back to that later. What resistor could be added to the circuit to reduce the total load resistance to 0.5 ohms and how should it be connected? Well, we currently have 2.5 ohms. We want our total resistance to be 0.5 ohms and they're asking us to do that by adding a resistor. Well, there's only one way that can happen. If you remember, whenever you add resistors in parallel, the resistance gets smaller. If you add them in series, it's just going to get bigger. So it must be that we have to add more resistors here or another resistor here in parallel to make our total resistance 0.5. So that's just what I'm writing there. And then we want our total resistance to be 0.5. We currently have 2.5. We need to find what we have to add in. So you can follow down that working and we end up getting that one to be 0.625. Right, part B is the stinker. So what power does the battery deliver to the load when this resistance is added? So this is asking about the new situation, okay? This is asking about when the load resistance is 0.5. So I'm going to ignore this working out for a minute to try and get the thought process across here. So if we have our new conditions, right? Oh, I'm not even on the page. Here we go, right? EMF is 6. We know our load resistance is 0.5. Do we know I yet? No, we don't. But the thing that we're actually missing here, I know I filled it in, it's because I've worked out already. We need to know this internal resistance in order to figure out the current that is flowing here. And once we get the current, then we can use P equals I squared R again to get the power. So we cannot get the current here because we don't have the internal resistance. So we don't know like how many volts are getting used up going through that, which is going to affect the voltage here, which is going to affect the current. So we have to use that first situation, right? So we know that the terminal PD is 5 volts when the resistance was 2.5 ohms. So we use that to figure out the current in that situation, which will allow us then to figure out what VR is. Okay, so our original situation was EMF of 6 volts, load resistance of 2.5, and we don't know we are. But we do know that the voltage across this is 5, so we can use these two together in V equals IR to work out that the current flowing in this situation is 2 amps. Once we know that, we can use this all together, because we've got, if the voltage here is 5, the lost volts, the volts that are used up getting through the power supply, must be 1, because these two are going to have to add up to give us 6. So we've got VI, we can figure out VR. So we use our first situation to figure out what the internal resistance is. So it's 0.5, which means now we can look at the new conditions. Now we know R is 0.5, we know the load resistance is 0.5, we know the EMF is 6. If we go into this, we can use E equals I, R plus R. So 6 equals current unknown. Big R is 0.5, VR is 0.5, so we can figure out that the current flowing now is 6 amps. And that makes sense that it's higher because the load resistance is lower. Now we've got the current, we can do P equals I squared R to get the power. That question is a stinker. I showed that a lot today in class, that my first attempt at this, like a few years ago, did not go well. It's just got scribbles all over it. And the reason is that I tried to do it without drawing these wee diagrams. So I cannot emphasize enough how much these wee drawn diagrams helps. Taking your time. I know I rushed. I feel like I'm speaking really fast, and probably not. But taking your time to break down the information in the question. Right, this is long enough, this video, so I'm going to end it there. Hopefully it has helped you. I will get it uploaded now. Bye!